Hi everyone, I just want to go over a few things with today's lab with you. So if you come to your calendar, so this is the week of the 31st, you will see that for the Monday you are supposed to be doing the conversion factors lab. And then on Wednesday we'll do the density lab. And these are both paper labs, so if you don't have your lab kit yet, no worries. And then these will both be due on Monday. Okay, so I would not wait until Sunday night to do these. I would try to jump on these during the week. That way you can talk to me if you have any questions. But first, let's just go over this conversion factors lab. So if you will come down to week 2, you will see this folder. And you'll see a couple things here. So the first thing you'll see is this video about significant figures. And then you will see the actual lab experiment. So that's the sheet that goes over sort of what you're going to be doing, and if there's a procedure, that will give you the procedure. And then you will see your report sheet. That's what you'll actually turn into me. So the first thing I would do is go ahead and download these two Word documents. Just make a folder for the lab, which you've probably already done, and go ahead and save these two. Okay, so I want to start out by just going over a few things in the lab experiment document. So this is broken down in sections A through, I think, E. So A, B, C, D, E. Oh, it actually goes all the way to G. Okay. So, sorry if you're getting nauseous from my scrolling. Okay, so we're going to start with A. And so if you take a look at this sheet and then we pop over to your actual report sheet, you'll see some questions, and then you'll see each section, so A, rounding. And if we come back to the experiment document, so the procedure document basically, you'll see A, rounding number. So those will match up. So it might be a good idea to kind of treat each section on its own. So kind of read through the rules for rounding, and then look at the samples, and then maybe hop over to this sheet and go through that. That might be a good way to do it. However, whatever your preference is, that's totally fine. Just a suggestion. Okay, so first let's talk about the first part, A. So rounding. Well, the very first thing I would do if I was you, in order for some of this to make sense, is before you even start on the rounding numbers, so you could pause me now and hop over to this video and watch the significant figures video. So she does a really good job going over Sig Figs, so I'm not going to go over that again because there's no reason to make you listen to it twice. So I would just pause this video now and go and watch this video, and that way you understand what Sig Figs are in case you've never dealt with them. And then once you're done with that, you can come back and listen to me some more. Okay, so first section is just rounding numbers. So if you grew up in the US and you're used to rounding numbers, it's probably the exact same way you learned as a kid. If you grew up somewhere else and maybe you use the odd and even system, that's not the one we use here. We end up using the less than 5 and greater than 5. You're probably familiar with that as well. But that's the one we're going to use. So if a number is less than 5, we know that it's going to make the number to its left go down. And a number, if it's 5 or greater, will make the number go up. So increase by 1, in other words. Okay, so hopefully you're pretty familiar with that already. But let's just look at an example or two. Okay, so this question asks us to round these numbers to 3 sig figs and then to 2 sig figs. Okay, so it gives us a couple numbers here. So let's just do 1 or 2 of these. So the first one, it gives us 75.6243. And the first thing it wants us to do, again, round to 3 sig figs. So with sig figs, when you have non-zero digits, we know that all non-zero digits are significant. So this makes it pretty easy on us. So all we have to do is count 1, 2, 3. That's 3 non-zero digits, so those are all significant. And what I like to do is once I find that digit that I'm going to be looking at to round, I'll put a little line under it. And you'll probably see that from time to time in other places. Okay, so I'll just underline the 6. And if you're doing several calculations, that's a good way to remember which digit you're supposed to be rounding to in the end, because you always want to wait and round at the very, very end. Okay, so we know that we have 3 sig figs. We want to have 3 sig figs. So we have 75.6243. So that means we're going to forget about the 2, the 4, and the 3. Okay, so we're going to forget about those. But the 2 tells us how to round the 6. So do we round it up or do we round it down? Well, the 2 is less than 5, so that means it would stay the same. I think earlier I said that you would round it lower. I may have misspoke there. So in other words, the 2 tells us to keep it the same. Okay, since it's less than 5, that means keep it the same. So to 3 sig figs, this number just becomes 75.6. Okay, so we don't change anything else. Okay, so what if, though, we want to round this to 2 sig figs? So how will we do that? So we'll come again and say, okay, the 7 is significant, the 5 is significant, and I just want 2. So I'll underline the 5, and that reminds me, okay, that's the digit I'm keeping. And then the 6, I know is greater than 5, and if it's greater than 5, I know that I need to round it up by 1. So that means the number 75, the 6 tells me to round that 5 up to a 6, and that becomes 76. Again, so if you're familiar with this system already, it's exactly what you learned. The only difference is now we're putting sig figs in with this. Okay, so let's look at the next one. So the next one, it asks us, okay, so again, 2 sig figs, 3 sig figs, and it gives us 0.528392. So we have many more digits than what we actually need. And oftentimes, your calculator, this is what you'll see from your calculator. Okay, so it'll give you way more digits. However you have it set, it'll give you way more digits than you need. Okay, so let's round this to 3. So the first thing we see is a 0. We have a leading 0. Okay, well, a leading 0, like this, is not a significant 0. Okay, so that would not count as one of our significant digits. So if we want to start counting significant digits, we'll start from the first non-zero, which in this case would be this 5. So 1, 2, 3. That takes us all the way to the 8. So I will underline the 8 to remind me that's where I'm keeping. That's the digit I'm keeping. Get the cursor out of the way for you. So now I want to look at the digit to the right of the 8. If it's less than 5, I keep it the same. If it's greater than 5, I round it up. In this case, it's less than 5. Okay, so I'll keep it the same. So my number becomes 0.528. Okay, so I just keep it the way it is. And basically all I'm doing here is just chopping off these other 3 that I don't need anymore. Okay, so what about 2? So what if I want to round this to 2? So again, the 0 doesn't count. The 5 and the 2 count. So I'll underline the 2. The 8 tells me to round up, so this becomes 0.53. Okay. The next one, so C, I have 600, so 387,600 in other words. And so I first want to round to 3 sig figs. Okay, so I know the 3, the 8, and the 7 are all significant, so the 7 is where I'll be stopping. The 6 tells me to round it up. Okay, so my 3 significant digits become 3, 8, and 8. But I can't lose the value of my number. Okay, so if I don't put these zeros in, then I just have 388. But that's not what I have. That's not the number. The number is 3,800, or 388,000. Okay, so I have to still include these zeros. And as long as there's no decimal here, okay, so as long as I don't have something like 0.0 there, no decimal, these are not significant, so they don't count. So they're trailing zeros with no decimal are not significant. So that means those 3 zeros don't count, and if I was counting sig for this number, I'd say 1, 2, 3, just the 3, the 8, and the 8. Okay? And now if I want to do the same thing but for 2, I'll keep the 3 and the 8. The 7 tells me to round up, so this becomes 390,000. And again, the same thing, I have to keep the zeros in order to keep, they're just placeholders. In other words, to keep the value of the number, I need to still put the placeholders in. And since there's no decimals, these 3 don't count, so I just have 2 sig figs. Okay, and the last one, So I just have 4. No decimal, no nothing. Okay, so the 4, if I want to make this 3 sig figs, okay, I can just add 0.00, because remember, if I have a decimal, the trailing zeros, these 2 zeros, now they count. Okay, so if I have a decimal, my trailing zeros count. And the same thing for 2. So if I just write 4.0, now that's 2 sig figs. Again, the decimal makes that trailing 0 count, whereas in the number above it, they don't count because there's no decimal. And in the one above this, the 0.53, the leading 0 does not count either. Again, it's just a placeholder. So any 0, that's just telling you the value of a digit. In other words, it's telling me that this is 5/10 and not 5, for instance, or not 500 or not 5,000ths. Okay, so all it's doing is telling me where that digit actually goes. So any 0 that's just a placeholder will never be significant. We don't have this example, but suppose we had something like, I'm just making up a number here, 503. Okay, this middle one is called a trap 0. Okay, that is also significant. So that's not just a placeholder anymore. Okay, this actually has value. Okay, so it's still significant. So if it's trapped or trailing with a decimal, those are both significant. If it's trailing with no decimal or leading, then it's not significant. Okay, the next part, part B. So this has to do with sig figs and calculations. Okay, so hopefully you watched the other video about each operation, but I'll go over it kind of quickly here with you again. So if I have multiplication and division, I will always keep the fewest amount of sig figs. And what I mean by that, so if 3.44 and 4.62, these both have 3 sig figs, 0.025 only has 2 sig figs, that means in my final answer, I will only want to keep 2 sig figs. Okay, and that's true for multiplication and division. So all you have to do, find the number that has the fewest number of sig figs, and that will tell you how many to keep in your final answer. And the only exception there is if you have something like a conversion factor. Okay, but just in general, you'll find the one with the fewest number of sig figs, and that's how many you keep in your final answer. So here you see that they went ahead and did this math for us, and we end up with this long number. Again, your calculator might tell you something like that. And since this 0.025 is only 2 sig figs, okay, we only keep 2 in this number. Okay, so we just keep the 3 and the 4. And again, notice we rounded here. Okay, so if we were doing my rounding trick, we would put our line there. The 5 tells us to round up, so our number becomes 0.034. With addition and subtraction, it gets a little more tricky. Okay, but it's not tough. Once you see it, it's no big deal. Okay, so if I'm doing multiplication, I'm sorry, I meant subtraction. I said division. Multiplication or subtraction, all you need to do, line up your decimals. Okay, so you see they have all their decimals nice in a line here, and that's the best way to do it if you're not sure. And once you get good at this, you don't have to do this anymore. Okay, but when you're starting out, this is the best way to do it. And what you want to do is you want to find the number that has the least places after the decimal. And the way I was taught is you draw a line like this. And that will tell you exactly where to round your answer. So the 2.11 only has 2 after the decimal. So I'll draw a line, and that tells me to chop all of my numbers after 2 places after the decimal. Okay, so in this case, it doesn't matter which has the fewest sig figs, nothing like that. The only thing that matters is which has the fewest after the decimal. So if the 2, for instance, was just 2, then I wouldn't keep any after the decimal. Okay? But since I have 2.11, that tells me to keep 2. So I'll come all the way down to my answer, and I see that the number to the left of my line is an 8. So that's my digit that I'm keeping. The 6 tells me to round up, so then the 8 becomes a 9. So you get to 106.29. These next couple sections, so C, D, E, These are all basically the same thing, but we're just looking at a different unit. So in this section, or these sections, we're talking about conversion factors, so kind of the big point of this lab. And I'm just going to kind of go through some examples with you, and then once you know the basics, you can apply it to any conversion factor that there is. So it doesn't just apply to one or the other. So if I show you how to do one, you'll basically know how to do all of them, given that you know, well, firstly, the metric system, so make sure you have a good handle on that so far. And then once you know some of the basic conversion factors, you can either look them up or they'll be given. But once you know how to use them, pretty much all the same. Okay, and the technique we're going to use to do this is called dimensional analysis. And I'm just going to sort of go through some examples, and I think that will help you pick it up pretty quickly. Okay, so I'm coming over to my notebook program where I can just draw for you guys. And we'll take a look at some examples. Let's see, I always like to use purple. Okay, so let's look at some examples here. Make sure I have the right pen. Okay. So there's some basic conversion factors, like the ones used just for the metric system. So you've probably learned one way to use the metric system where you know maybe this King Henry died Monday, don't call me, or maybe you said drinking chocolate milk, however you did it. So you probably know one method where you bounce your decimal around. And that works great when you're only dealing with the 7 units or so. Okay, but when you start to get into things like nano, which is 10 to the minus 9, okay, that's not really going to work anymore. You're going to be moving a lot of decimals. Okay, so the better way to do this is to use a conversion factor. And basically, a conversion factor will tell you something like this. So it might tell you that 1 meter is equal to, sorry, let's do this the other way around. Sometimes it's a little tricky when you think about this. So this will tell you 1 kilometer is equal to 1,000 meters. I almost said it backwards. That's why I paused for a moment. Okay, so we know this is true. So this is one way of writing a conversion factor. Okay, but the more useful way of writing it is actually something like this. So for every 1 kilometer, I have 1,000 meters. Okay, and I can also write this the other way around. So I could say that for 1,000 meters, that gives me 1 kilometer. Okay, so this is the same conversion factor. The only thing that changes is its use. Okay, so all 3 of these are telling me the exact same information. And it's the same information that I would get from moving my decimal. Okay, so if I move it 1, 2, 3, so going from meters to kilometers, which you may have done that technique before, we know that that would be, either reducing by 1,000 or increasing by 1,000. Okay, so it's all the same information. But this is much more useful when it comes to doing long calculations where you're maybe converting from, nanograms to grams or milligrams to grams, whatever it is. Okay, this is the more useful way of doing it. And the way that we use these is in what we call dimensional analysis. And I'm just going to pick some random numbers and just show you kind of one technique for doing this. So using our kilometers and meters example here. So let's say that, for instance, maybe we have 5, let's start with the one on the, let's say we have 5 meters. Okay. And suppose we want to go from 5 meters, and we don't know how many kilometers that is. Now this is probably an easy one to do in your head, but again, once these numbers start to get more complex and you're doing a series of calculations, okay, it gets a little bit tougher. So if we want to use dimensional analysis, this is what we would do. So we would say 5 meters, and I want to end up with kilometers. And the principle behind dimensional analysis is that I'm going to use my units to go from the information that I have to the information that I'm looking for. Okay, so I'll go from 5 meters and I want to go to kilometers. And there's a couple ways of writing out dimensional analysis. I'm going to show you the way that I use, and I'll show you kind of a second way as well. So this is the way I do it. So when I learned it, this is how it was taught, and we call this the train track method. Okay, so it's dimensional analysis, and this particular version of it is called the train track method. And what this does is it allows you to do a series of calculations in a row and sort of keep everything organized. So if I want to go from 5 meters and I want to know how many kilometers that is, I need to use my conversion factor. So how do I know which one to use? How do I know whether to use 1 kilometer over 1,000 meters? Or do I use 1,000 meters over 1 kilometer? Well, the answer to that is I want to use the conversion factor that ends up canceling out the unit and leaves me with the unit that I want. So here I have meters, but I want to end up with kilometers. Okay, so what I'll do then is what goes on the bottom is the meter part. So I'll use this one. Okay, so I'll say that for 1 kilometer or kilometer, there's 1,000 meters. Okay, so in other words, basically I'm taking 5 and I'm dividing by 1,000. Okay, so take your calculator, say 5 divided by 1,000. That will give us 0 point. And always start your numbers with a number. So sometimes I'll see students do this. So you'll say, this is my answer. Okay, but what we've done here is we haven't started our number with a number. We've started our number with a decimal. That doesn't work. So what you want to do is you just want to throw a 0 up there. Okay, and it's just a placeholder. It doesn't affect anything. It just makes it look nicer. Okay, so this would be our answer. Okay, and now suppose, and make sure we write our unit. And if we weren't sure what unit, or if we wanted to double check that we done it correctly, what we can do is we can actually cancel out our units. So anything on the top and the bottom that's the same will cancel out. So meters will cancel with meters, and we're left with kilometers, and that's what we were looking for. Okay, so that worked out. And if for some reason our unit didn't cancel out properly, then we know we've made a mistake. And we can go back and we can figure out where that mistake is based on our units. Okay, go back to purple. And suppose we were going the other way around. So now suppose we had 5 kilometers, and we wanted to know how many meters is that. Okay, so now I'll start my dimensional analysis like this. So I'll say 5 kilometers. Okay, and now I want to end up with meters, so I'll use the one that lets me end up with meters. So that would be the second one. Okay, so for 1,000 meters, that's 1 kilometer. Okay, so here I'm just multiplying 5 by 1,000. So I end up with 5,000. Okay, 5,000 what? Well, if I'm not sure, I can go back. I can check my units. So kilometers with kilometers, left with meters. So 5,000 meters. Okay, and the reason you might want to do something like this is this. So suppose I want to know how many. So suppose I want to go from 5 meters. Let's use a different number different than 5. I've used 5 a bunch. So let's say I wanted to go from 2.3 meters. And I want to know how many inches is that. So now I'm going from metric system to inches. Okay, so I'm going from meters to inches. So maybe I can't remember exactly how many meters is 1 inch. But maybe I do know this. I know that there's 2.54 centimeters is 1 inch. That's my conversion factor. So I could also write it like this. 2.54 centimeters gives me 1 inch. Okay, and me personally, this is the one that I know. I don't necessarily know how many meters there is in 1 inch, but I do know that there's 2.54 centimeters because that's an easy number for me to remember. Okay, but I have meters, so I can't just go from, because I don't know that, I can't remember it, or I could look it up. I mean, we all know we could look it up, but suppose this is the one we know, or this is the one we're given. Let's say that. So what we can do now is we can actually string these together. So I'll zoom in a little bit more for you. Okay, so 2.3 meters, and I'll set up my dimensional analysis. Okay, but I just said centimeters to inches. Okay, so I have to remember how many meters are in a centimeter. Okay, so if we were doing it this way, we know we would just move 1, 2 to the right. Okay, but we're not going to do it that way. What we're going to do is we're going to say that for 1 meter, that's equal to 100 centimeters. So that's our conversion factor. Okay, so and a way of rationalizing this is centimeters is a smaller unit than a meter, so our number should be going up. It should be getting bigger. Okay, so for every 1 meter, I have 100 centimeters. Okay, so this calculation would leave me with centimeters, but I want inches. Okay, so I'll put another one here, and I wrote down this conversion factor for centimeters to inches. So now I can write, okay, for every 1 inch, there's 2.54 centimeters. And I'm going to erase this just for now, so we don't need it really anymore. Okay, and now I can check my unit. So meters cancel with meters, centimeters cancel with centimeters, and I'm left with inches. Okay, so hopefully you can see what I'm doing is I'm letting the unit guide me in how to establish my conversions. So which conversion factor I use? Do I use centimeters over meters? Do I use meters over centimeters? And that might not be so obvious if you're just trying to simply type it into a calculator or solve it in your head. But if you write it out like this, I think you'll see that now I know exactly which way to put everything. Okay, so again, I just made these numbers up. So if we run this calculation, and now what you need to do is you want to say, I'm going to pull a different color out for this. Choose red. So what I want to do is I want to say this times this times this, and then divide by everything on the bottom. So then divide by this and divide by this. Okay, so you can also do each step individually, but the longer that these get, the easier it is to just multiply everything across the top and divide individually by everything on the bottom. So to solve this, I'm going to say 2.3 times 100. And you can honestly forget about the ones. You don't have to say times 1 and divided by 1. It's just unnecessary. Okay, and then I can say divided by 2.54. And this gives me, sorry, I won't write that in red. I'll grab a different color. Okay, so my answer here would be 90.5511. And then to use correct Sig Figs, it only gave me 2 in the beginning. Okay, so this is not the best example here. But so I would keep 2 Sig Figs in my calculation. So these are conversion factors, so those are considered to have infinite Sig Figs. But since my given number was 2.3, I know I have 2, so I'll round based on the 5. So this will become 91 inches. Let's write that a little bit neater. And my unit is inches. Okay, sorry, that's a 1, not a weird 0. Okay, so hopefully that helps you in understanding how to use conversion factors. And what I want to do is I want to write this out one other way, because you might be more comfortable seeing it this way. So some people like to write it like this, 2.3, and then use x's for the multiplication. So times 100 centimeters over 1 meter, and then times 1 inch over 2.54 centimeters. Okay, some people, and there's absolutely no difference in the calculation. It makes no difference whatsoever. Whichever way is better for you, Okay, that's fine. So the only difference here is that the vertical lines here tell you to multiply, the horizontal line tells you to divide. Here, the x tells me to multiply, and the line, of course, tells me to divide. Okay, but that's absolutely the only difference. You'll come up with the exact same answer. So don't worry about that. I prefer the train track method, but I have noticed more recently a lot of students prefer to use the x's and then the traditional fractions. It makes zero difference. Okay, so whichever one you like better, choose that one. To me, using the train track is much easier, but it really makes no difference whatsoever. Okay, so that's conversion factors. And if we go back to our report here, okay, so if we come back to our report sheet, just 1 second to find my mouse. There we go. Okay, so we have conversion factors for length. Okay, so that's part C. Part D is for volume. And then lastly for E is for mass. But what you'll see is going through this, they all work exactly the same. Okay, so the only thing changing there is your unit. So whether you're dealing with a unit of volume, a unit of mass, a unit of length, it's all the same. Okay. One more thing I would want to say here is that if a unit is, for instance, cubed, so I'm trying to find a good place to do this. So let me grab green maybe. Okay, so suppose this was cubic meters. You would want to cube the whole thing. Okay, so I want to do something like this. Okay, so if something is a squared unit or a cubed unit, you would want to cube or square the entire conversion factor. Okay, so this would become 100 centimeters and the whole thing would be cubed. Okay, so don't let that confuse you. It's just if you run into a unit that's squared or cubed, okay, make sure you cube or square or whatever the power is, the entire conversion. Okay, hopefully I didn't lose anyone by pointing that out. I just wanted you to know, in case you run into that situation, that's what's going on. I want to undo all that because I would like to post this sheet for you guys, and that doesn't look all that great. Okay, that looks better. Okay, so let's go back over to our report here. Okay, so all three conversion sections should work exactly the same. And then we get down into percent by mass. Okay, so whenever you're dealing with calculating percents, no matter what percentage it is, so any percent will always be the part. Let me fold my computer back again. Here we go. Any percent will always be the part divided by the whole, and then times 100%. Okay, so if I want to know the mass percent of something, so that's what this section is talking about. So I don't know if I mentioned that, but we're talking about percent by mass. Okay. So suppose I had 10 grams of sodium chloride. Okay. And I wanted to know, or suppose, let's say this, I had a 10-gram mixture of, let's say, 10 grams of sodium chloride and sand. And this is kind of something you'll do later. So it's a mixture of table salt and sand. And it's 10 grams, and then through some calculation I find out that that is 2 grams table salt. Okay? And suppose I want to know what percentage of this sample is table salt. So I'll take the part, the 2 grams is my part, since that's what I'm interested in, over the whole. The whole sample is the 10 grams, okay, times 100%. And that will tell me the percent by mass. So I'll just say 2 divided by 10, of course 0.2, times 100%, which is of course 20. So my answer here would be 20%, which is easy enough to do in our heads, but that's how you do it. Okay, so it's always just the part over the whole. And that it comes to, if you're talking about percent by volume, this is percent by mass. But if you're talking about mole fraction, there's lots of these different things that you'll get into if you keep going with chemistry. But for now, this is just percent by mass, which is the part you're interested in, so the mass you're interested in, divided by the entire mass of the sample. So the part divided by the whole times 100%. And so whenever you're looking for percentages or fractions, if you will remember that part over the whole, you're good to go. Okay, and that's always true. So if you're looking for what fraction of something is this, or what percentage of something is this, always the part over the whole. Okay, and that's really all there is to that. Okay, so coming back to your report sheet here, not your report sheet, but the experiment sheet, you get down into converting temperature, and it goes from Fahrenheit to Celsius, or Celsius to Fahrenheit, excuse me, Celsius to Fahrenheit to Celsius, and then from Celsius to Kelvin. So Celsius to Kelvin is the easiest calculation. So you just take your Celsius temperature, add 273, or take your Kelvin temperature and subtract 273. And that's because all they've done between those two scales is shifted one up by 273. That's literally the only difference. The other two are a little more complicated, but not difficult either. They're, again, very simple calculations. So if I know Celsius and I want Fahrenheit, this is the calculation I use. So notice here I say 1.8 times my temperature in Celsius plus 32. And it's very important here to maintain your order of operation. Okay, so remember to distribute, so to multiply first, and then do your addition and subtraction. So first multiply 1.8 times your temperature in Celsius, and then add 32. Okay, and then for Fahrenheit to Celsius, so if I know Fahrenheit and I want Celsius, this is the one I use. So I'll subtract 32 from my temperature in Fahrenheit, and then divide by 1.8. So make sure you do it in that order. So you notice this is always written in parentheses. Okay, that lets you know to do it first. So even though subtraction comes later in the order of operations, since it's in parentheses, you need to do that first and then divide by 1.8. If you try to, for instance, divide the temperature in Fahrenheit by 1.8 and then subtract 32, you're not going to end up with the right answer. Okay, so make sure that you follow your order of operations, do your parentheses first, your multiplication first, then your division, multiplication, then your addition and subtraction. So just follow that order of operations, same one you learned a long time ago, I'm sure, and you'll end up with the right answer. But if you try to go out of order, then you'll end up with an incorrect number. Okay. Okay, so the report goes on and it gives you some tasks to do, and then you will come to your report sheet, and there's a section to put each one of your answers. I will let you go over that on your own, because I think now that you know the basic rules, now that we've gone over the basic rules, you should be able to handle this, no problem. And make sure you go over the discussion and everything on your own. And if you need any help with this, please feel free to email me, come see me in my office hours, and I can help you with anything that you would like to go over with in more detail, or anything maybe where I made a mistake and maybe I didn't tell you the right thing, or if you just have a question in general about anything, please come see me. And so once you are finished putting all of your answers into the report sheet, if you will come back to the lab section here, there's a spot at the bottom for you to turn this in. The only thing I need back from you is this report sheet. Okay, and remember that will be due on Monday. Okay, so again, if you have any questions, please come see me and we will talk about it.